Calculating cell EMFs can be a little bit confusing at first, so in this video I'm going to show you a much more logical approach. And by the end, not only will you be able to calculate cell EMFs more confidently, but you'll also be able to work out unknown electrode potentials and explain how changes in conditions will affect the EMF of a cell. But let's start off by having a look at what EMF actually is. Well, here we have an electrochemical cell made up of two half cells, and different half cells have different tendencies to lose electrons. In this zinc and copper cell, zinc atoms will lose their electrons much more readily than copper atoms will do, which means zinc has a more negative standard electrode potential, and that difference in tendency to lose electrons is what drives electrons around the external circuit. So the cell EMF, or electromotive force, is simply the difference in electric potential between the two half cells. In other words, the potential difference between them. It essentially measures the driving force pushing electrons through that external circuit. The greater the EMF, the greater the driving force, and the more strongly electrons are pushed around the circuit. So now we can start to quantify that difference and calculate the EMF of a cell. Now, often in exam questions, you'll be given an electrochemical series and asked to calculate the EMF of a cell made from two of the listed half cells. In order to do this, you first need to be able to identify which of the two half cells would be oxidized and which would be reduced. And what I'd normally do here is just highlight the two half cells you've been given in the question, just to help you focus in on the relevant values. Here, I'm going to stick with my zinc copper cell. Now, the key idea is this. The more negative electrode potential is always the one that gets oxidized. And that's because the more negative value tells us that that half cell has a greater tendency to lose electrons. Remember oil rig, oxidation is loss of electrons, reduction is gain. And if we're drawing or representing the electrochemical cell, the more negative half cell, the one that's been oxidized, should always go on the left-hand side. The more positive electrode potential must therefore be the one that is going to be reduced, and that's because the more positive value tells us the half cell has a greater tendency to gain electrons. And so when representing the cell, the more positive half cell, the one that's being reduced, goes on the right-hand side. So oxidation always occurs at the half cell with the more negative electrode potential, and reduction will always occur at the half cell with the more positive electrode potential. But this is where electrochemical series can often trip people up, because the half equations are always written as reduction half equations, which is fine until you remember one of your electrodes is actually going to be oxidized. Now, when calculating EMF, exam questions also often ask you to write half equations for the reactions that are happening at each electrode. And this is where we need to remember an electrochemical series will always give us the reduction half equations. So the half cell with the more negative electrode potential is the one that gets oxidized, and this is going to become our negative electrode. Therefore, we can't just use the half equation directly from the electrochemical series. We need to reverse it so that it is showing oxidation. And that's easy enough to do. You just take what was on the left of the arrow and put it on the right, and what's on the right then goes on the left. So in this case, I now have the zinc solid on the left of my equation going to the zinc ions and electrons as the products on the right, clearly showing oxidation. Now thankfully, the positive electrode is far more straightforward, because the positive electrode is where reduction happens, and so we can literally just take the half equation straight from the electrochemical series and use it as the half equation for our positive electrode. So in this case, we're going to keep the copper ions and electrons on the left and our copper atom on the right. And now that we've got all that in place, we can finally look at calculating the EMF of the cell. And the important thing to remember here is that the EMF is just the difference in electrode potential between the two half cells. So we're not adding anything together, we're not doing anything complicated, we're literally just finding the difference between them. So the equation that we use is this. The cell potential, or EMF, is equal to the electrode potential of the reduction half cell minus the electrode potential of the oxidation half cell. Let's have a look at this in action with our zinc and copper cell we've been using. From the electrochemical series, zinc has the more negative electrode potential, so that's the one that's going to be oxidized. Copper, with its more positive electrode potential, is the one that's going to be reduced. And now we can just plug the values into our equation. So the EMF is going to be equal to 0.34, our reduction electrode potential, minus 0.76, our oxidation electrode potential, which gives us an EMF of plus 1.10 volts. And notice what's happening here. We're not memorizing a trick, we're just consistently applying the same idea. The EMF is the difference between the two electrode potentials. And this is where students often go wrong. You don't need to flip any values from the electrochemical series. You just subtract the oxidation electrode potential from the reduction electrode potential. And once you've got that process nailed, EMF questions just become routine. However, sometimes exam papers will give you the cell EMF and one electrode potential and ask you to calculate the other electrode potential, as you can see here. Now the good news is that they usually tell you which electrode is the positive electrode and which one is the negative electrode. In this case, we're told that electrode B is the negative electrode. The not so good news is that they don't tell you what that means in terms of oxidation or reduction. They expect you to know that oxidation always occurs at the negative electrode and reduction always occurs at the positive electrode. So now we can just use our same equation for calculating the EMF of a cell. We just need to do some rearranging. Now, if the question wanted the electrode potential of the positive electrode, then we'd need the reduction half cell as the subject of the equation. So to do that, we just add the oxidation electrode potential to both sides. That leaves us with the reduction electrode potential being equal to the EMF of the cell plus the oxidation electrode potential. But in this particular question, we're actually asked to find the electrode potential of the negative electrode. So we need the electrode potential for the oxidation half cell as the subject. So if we add the electrode potential for the oxidation half cell to both sides of our equation and then subtract the electrode potential for the cell, or the EMF, from both sides, we're left with the electrode potential for the oxidation half cell being equal to the electrode potential for the reduction half cell minus the EMF. Now we can then just plug in our values from the question into this rearranged equation. So the electrode potential for the negative electrode, our oxidation half cell, is equal to minus 0.15 minus 2.90. Note that it's really important we keep any and all signs for values exactly as they are. There is never any reason to change signs. This gives us a correct value of minus 3.05 volts. And notice the answer we've ended up with is very negative, which makes sense because this is our oxidation half cell, which means it should have a more negative electrode potential. So far, we've been working with standard electrode potentials, fixed values under standard conditions. But in real cells, those conditions can change, and when they do, the EMF can change as well. So the next question is, what actually affects the EMF of a cell? Well, we know that the EMF of a cell is the difference in electric potential between the two half cells, and that each electrode potential depends on the position of the equilibrium within that half cell. So if we change anything that affects the equilibrium position, we're going to change the EMF. Now in exams, there are three factors you need to know: concentration, pressure, and surface area. But only two of these actually affect the EMF of a cell. So let's start with concentration, using our zinc copper cell as an example. If we increase the concentration of zinc ions, Le Chatelier's principle tells us that the system will oppose that change. So the equilibrium in the zinc half cell would shift. Now in this case, it would shift towards the zinc metal, to the left. But the key question is, what does that actually do to the electrode potential? Well, the further the equilibrium lies towards ions and electrons, the more negative the electrode potential becomes. Here, we've shifted away from that, so the electrode potential would actually become less negative or more positive, and that would change the EMF. In this case, the EMF decreases. But we don't need to memorize separate cases here. We just use the same idea. Changing concentration changes the position of the equilibrium, which changes the electrode potential, which changes the EMF. So increasing the concentration at the negative electrode shifts the equilibrium in a way that makes the electrode potential less negative, and so that would reduce the EMF. Whereas increasing concentration at the positive electrode makes the electrode potential more positive, and that would result in an increase in the EMF. So it all comes back to one idea. EMF is the difference between two electrode potentials, and anything that changes those potentials will change the EMF. Now let's have a look at our next factor, pressure. Now the key thing about pressure is that it will only affect cells that contain at least one gas within a half cell. Here I'm going to use a hydrogen silver cell with the hydrogen half cell obviously containing a gas. Just as with concentration, a change in the pressure of a gas is going to affect the equilibrium position within the half cell. Now that changes the electrode potential and therefore will change the EMF of the cell. And this chain of thought is important when asked to explain changes to EMF in exam questions. So what happens if we were to decrease the pressure? Well, Le Chatelier's principle tells us the system would counteract that change by trying to increase the pressure, shifting the position of the equilibrium towards the side with the gas, to the left in this example. And that's actually favouring the reduction reaction within that half cell, and that would make the electrode potential less negative or more positive, decreasing the EMF of the cell. Now we're just using the exact same idea as before. How does the changing condition affect the position of the equilibrium? And what does that do to the electrode potential? And therefore what does that do to the EMF of the cell? All the while highlighting the importance of being able to identify which electrode is which from standard electrode potential values. Okay, so we've covered concentration and pressure. That just leaves the third variable that you could be asked about, which is how changing the surface area of the electrode affects the EMF of the cell. And this one's a trap, because it doesn't. Changing the surface area of the electrode would affect the rate of both the forward and reverse reaction equally within the half cell. So the equilibrium may end up being reached faster or more slowly, but the position of the equilibrium itself wouldn't change. Make sure to keep an eye out for questions asking about this in the exam, because it does catch some students out. So in this lesson, we've seen what EMF represents, how to calculate it, and how changes in conditions can affect it. Next, we'll look at salt bridges and how they allow charge to flow and complete the circuit in electrochemical cells.